or forces could be repulsive. That's when I have two like charges. Okay? Now, whereas attraction stabilizes, repulsion destabilizes. So when the molecules have a choice, which they do, they will choose to be more stable. So they'll orient themselves spontaneously, so we only exercise forces of attraction. The delta plus will navigate towards the delta minus in another molecule. The delta minus will navigate towards the delta plus in a molecule. You will never get a scenario where the two Brs are next to each other, or the two H's are next to each other. That is not going to spontaneously happen. Nature likes low energy. Nature likes stability. So the spontaneous arrangement is to set them up so the positive dipoles align with the negative dipoles. So the bond that exists between polar molecules, the bonds that exist between polar molecules are dipole-dipole bonds. Okay? Well, how strong are they? Well, unlike the case where we're dealing with sodium chloride or magnesium oxide, where there are finite, as we would call them, whole number charges, which really, again, we speak of it as a whole number 1, 2, or 3, like in aluminum 3+. And really, those numbers are taken as the Faraday number, if you will, right? This is the Coulombic charge. But even if I consider them as 1, 2, and 3, which are big numbers on the scale, a delta plus and a delta minus, those are much smaller. Right? That's 0.1 plus, or 0.4 plus, and 0.4 minus. Those numbers are much smaller than a 1, or 2, or a 3. A 1 plus is in sodium plus, or 1 minus is in Cl minus, or a 2 plus is in magnesium 2 plus, a 2 minus for O2 minus, a 3 plus for Al3 plus, a 3 minus for N3 minus, right? Those are big numbers, those are big charges. Therefore, the force of attraction between those, Q plus and Q minus, that's a big force of attraction, strong bond. Those are weak, because we're dealing with small dipoles. You multiply two big numbers, you get a big number. You multiply two small numbers, you get a small number. Right? So what that means is the force of attraction between one polar molecule and another, where we're dealing with dipole-dipole attraction, those forces of attraction are weak. I mean, they're weak. So what's the consequence then? The consequence is, if they're weak, they're easy to overcome. Which means I don't have to spend a lot of thermal energy to overcome them. So their melting points are low. For many of them, their boiling points are low. HBr is a gas at room temperature, which means 25 degrees Celsius room temperature provides enough of a thermal punch to not only melt solid HBr, but to boil it, to overcome all the intermolecular forces. Those intermolecular forces are going to be weak, and of course they are, because they're just dipole-dipole. Okay? Now, obviously, as the polarity of the molecule goes up, so the dipoles go up, the force of attraction, the intermolecular force, will go up, and the boiling point will rise as well. That has to be balanced against the mass of the particle. Because as the mass gets greater, the molecule gets heavier, and as the molecule gets heavier, it means my amount of energy I need to melt and boil it will also go up. So what would I expect then for molecules that have dipole-dipole bonds between them? I would expect low melting points, low boiling points. I'd expect them to be either liquids or gases at room temperature. Right? I wouldn't expect them to be solid at room temperature. Not unless they were particularly heavy. Right? Because you have to remember, Mass is also important because fundamentally phase changes like melting and boiling involve increasing the mobility of the particles. And if you're big and heavy, you're hard to move. And I'll have to put in more energy to move you. So dipole-dipole bonded compounds tend to have low melting points, low boiling points. They tend, when they're at room temperature, to either be liquids or gases. In fact, they tend to be volatile liquids. Okay? Let's talk about another category of molecular forces. Let's talk about hydrogen bonds. So, a hydrogen bond is a rather unique version of a dipole-dipole bond. I will begin by saying that all bonds in chemistry, so all bonds in chemistry are electrostatic in nature. So what does that mean? All bonds in chemistry arise between something positive and something negative. We've certainly seen that with ionic bonds. Okay? Cation, anion, Gauge ions, force of attraction, plus and minus. Dipole-dipole bonds. A negative dipole on the Br and HBr, a positive dipole on the H in HBr. Force of attraction, dipole-dipole bond, electrostatic. In fact, the very nature of a covalent bond involves the attraction between the nuclei of the two atoms and the electron share between them. It is the nuclear electron attraction that keeps the bond together. Electrostatic. So the hydrogen bond really is a unique subset of the dipole-dipole bonds. So what does that mean? It turns out that hydrogen bonds arise whenever there's an H attached to X, where X is either nitrogen, oxygen, or fluorine. Now, let me just break here this point. There is now a modest, well, there's now a convincing bit of evidence in the literature that suggests beyond NO and F, you can also include sulfur. So there is some hydrogen bonding that is observed between when X is equal to sulfur as well. For the purpose of this discussion, we're going to ignore that. Okay? So we are going to limit our discussion to why hydrogen bonding arises when we have H attached to either nitrogen, oxygen, or fluorine. Now, what I also will say is that a hydrogen bond is also a sandwich in which it is the attraction between, so I must have an H covalently bound to N or F in one molecule, and then N or F in another molecule. This dotted line is the hydrogen bond. This is the hydrogen bond. It is the bond that exists in the unique condition when there is a hydrogen attached to either N or F in one molecule, and then an N or F available in another molecule. So the hydrogen bond is a sandwich, which the H is the meat, if you know, vegetarian. Okay? And the X's are the bonds. The X's don't have to be the same. I can have N in one and O in the other, and so on. Okay? Well, what does that happen? Okay? Well, certainly N, O, and F are electronegative elements. So there's going to be a delta minus here, a delta plus here, a delta minus on that one. So it makes perfect sense that there'll be a force of attraction. That's a dipole-dipole bond. But why did I just call it dipole-dipole? Why is it so special? Right? Why is it so special to be called a separate class? And the answer is because Hn, O, and F are unique. Let's explore that for a second. H is the smallest element that bonds. Which means if I put a delta plus charge on that H, it is on a very small atom, and therefore the intensity of the charge is going to be huge. Right? So if I have a 1 plus charge on a particle that big, and a 1 plus charge on a particle that big, it's exactly the same charge. But the force field around that particle is massive. The concentration of charge is massive. The charge density is huge. So really, if I took this particle, right, and then I took this one, and I separated them, and I stood at the back of the room, and if such a thing were possible, and I threw a negative particle towards them, the negative particle is going to gravitate to this. Okay? Even though it's the same charge, the intensity of the charge density, which is the charge over the radius squared, the charge density, well, it's proportional to that anyway. The charge density is going to be massive. Force field around it is going to be massive. Okay. But we already saw I can have H attached to Br, and there'll be a delta plus charge on that one as well. Right? Yeah. There'll be a delta plus charge on that one as well. So why are we so excited about this scenario? Well, the three most electronegative elements in the periodic table are N, O, and F. Right? The three most electronegative elements in the periodic table are N, O, and F. Which means when these elements, when this X pulls electrons, it pulls it mightily. So the dipole on those H and those X's, that dipole is huge. So it's not like an HBr or an HS dipole. This is a massive dipole. So the Q term is already going to be high. Add to that, these are very high dipoles on a very small atom, massive charge density. But not only are N, O, and F the most electronegative elements in the periodic table, they are the smallest most electronegative elements in the periodic table. Right? F is the world's most electronegative element. And F is on the far right, if you ignore the noble gases, it's on the far right of the periodic table. It's a very small atom. Right next to it is O. Right next to O is N. So not only is the dipole on the X, N, or F very, very high, but these are particles that are very, very small. So the charge density on the N, O, or F is massive. So what am I looking at? I am looking at a huge positive dipole attracted with a very large charge density, attracted to a huge negative dipole with a very high charge density. So the net effect is that the force of attraction between them is going to be massive. And it is typically 1 or 2 orders of magnitude stronger than what you would see if this scenario did not exist. So we have to deal with those kinds of dipole-dipole bonds separately. We're going to call those hydrogen bonds. Okay? Now, the hydrogen bond is also kind of interesting, and that's another reason why N or F are in play, because the hydrogen bond is aligned along the lone pairs of electrons. So for example, if I look at, say, ammonia, so this is the shape of the ammonia molecule, there is a lone pair of electrons on the N here, in the sp3 hybridized orbital. That is where dipole that is where the hydrogen bond forms. So it forms along the lone pair, right, from the nitrogen. And then if there was another NH3 here, then in another ammonia molecule, this is where the hydrogen bond would exist. Okay? So the dipole, the hydrogen bond, forms along the line, the axis, if you will, of the lone pair of the donor atom. So if I ask you, how many hydrogen bonds can a molecule of ammonia form? Well, I can certainly form one using the lone pair on the end to the H on another ammonia molecule. But in each one of these H's could in turn form hydrogen bonds with the lone pair of an ammonia. Right? Hydrogen bonds with the lone pair of an ammonia, hydrogen bonds with the lone pair of an ammonia. Right? And these are the hydrogen bonds. So ammonia can form 4 hydrogen bonds per molecule. This is going to become an important point because if I asked you, what about a primary amine? Well, primary amines can only form, if I have an R group, primary amines can only form 3 hydrogen bonds per molecule. 2 via the H's on the end, because I need to have H on the end, and 1 via the lone pair. What if I had a secondary amine? Well, a secondary amine could only form 2 hydrogen bonds per molecule. Tertiary amine? If the tertiary amine is a sample of the pure tertiary amine, so that the other molecule also does not have H's on it, right? If I'm dealing with a sample of tertiary amine, then the tertiary amine, there are no hydrogen bonds. Now, there'll be dipole-dipole bonds, because this N is delta minus, and this R is delta plus. So I'll have a dipole-dipole bond, but that's not going to be a hydrogen bond. Agreed? So immediately then, I can ask you, look, if I take a sample of this compound, if I look at the isomers of that compound, so this is one propanamine. If I look at this compound, that is N-methylethanamine, which is an isomer, and I look at this compound, which is N-N-dimethylmethanamine. These are isomers, which means the masses are exactly the same. And yet, that one has a very high boiling point and a very high melting point. This one, so if I call this A, B, and C, what I would find is that if I'm looking at melting point, A has a higher melting point than B, and then there's a much lower melting point for C. If I were looking at boiling point, I'd see exactly the same thing. Why is that? Well, in A, there are 3 hydrogen bonds per molecule. Right? So we said, remember now, the physical properties depend upon the nature of the bond, how strong they are, and hydrogen bond are about the same. It also depends upon the number of those bonds and the mass of the molecule. So mass is a non-issue. These are isomers. The nature of the bond, the strength of the bond, is a non-issue. They're all hydrogen, well, these are hydrogen bonds. The issue then becomes the number of those bonds. And what you find is this has 3 hydrogen bonds per molecule, a lot more strong bonds to break, more thermal energy to break them, higher melting point, higher boiling point. This only has 2. One via the lone pair, one via the H at the end. So there are fewer strong bonds to break, less energy to pay, lower melting point, lower boiling point. This has no hydrogen bonds. We're now dipole-dipole territory. Okay? Dipole-dipole bonds are much weaker, so I have much less energy to spend. So there would be a certain difference between melting point and boiling point, between A and B, but a bigger difference. because I'm dropping off the hydrogen bond radar down to dipole-dipole, which are typically 10 to 50 times weaker than hydrogen bonds. I want to make a point here too. I'm getting close to the end of this lecture. If I look at three compounds, let's look at H. So compound at boiling point. If I look at water and I look at methanol and I look at ethanol, and I look at the boiling points, and I'm sorry, I don't remember the melting points offhand. The boiling point of water in degrees Celsius is 100. Methanol, 65. Ethanol, 78. So let's explain that for a second. There are two things to account for. Let's do this one first. Why is it that there is a 13-degree difference in boiling point between methanol and ethanol? And again, when you're asked the question in science, organic chemistry, nobody wants your opinion. Nobody wants your gut feeling. No, we're not guessing. There are things that affect the boiling point. What affects the boiling point? The nature, so it's the bond, it is the nature of the bond, and the number of the bonds, and the mass. Right? Those are our culprits. So when I asked you to explain why does ethanol have a higher boiling point than methanol, this is not a guessing game. If I have command of the knowledge that the boiling point and the melting point depend upon the nature and number of bonds and the mass of the molecule, that is what I go to. Okay, what is the nature of the bond between one methanol molecule and the other? Methanol has H attached to O. Hydrogen bond. Well, so does ethanol. So the nature of the bond is a wash. Okay. What about the number of bonds? Well, but the alcohols are all R, O, H. And there are two lone pairs of electrons on the O. So how many hydrogen bonds per molecule can an alcohol form? Oh, 3. One via the H that's attached to the O, and that's going to form along the lone pair of another alcohol molecule. And then one via each of the lone pairs, which would bond to the alcohols of other molecules. Okay? So each alcohol will form 3 hydrogen bonds per molecule. Right? Which means this is a non-option. It's a moot point for alcohols. So what's the difference between methanol and ethanol? Mass. So if I were to put, if I was smart, I'd put another column in here. And I'd say, I would say the molar mass, and then I would put the boiling point. Right, so the molar mass of water is 18, and this is grams per mole. The molar mass of methanol is 12, 16, 32, and ethanol would be 46. And then my boiling point is 100, 65, and 78. Okay, so methanol, well, ethanol is heavier than methanol. So I would require more thermal energy to lift an ethanol out of the container, right? If I'm lifting molecule by molecule out, right, the heavier that molecule is, the more energy to pluck it out. Right? The strength of the bonds and the number of the bonds are the same for ethanol and methanol. The difference is the mass of the compound. Heavier things require more energy to be lifted. So I've got to spend more energy higher the boiling point. So I can explain this. Right? Difference in mass, heavier compound, more energy to be put in, higher boiling point. Well, there's a problem here. because water is almost half the mass of methanol. So even though it's lighter, its boiling point is heavier, which is exactly the wrong argument, because we saw it work the other way here. So why does the lighter water molecule have a higher boiling point? Why am I spending more energy to lift water out of the water phase than to lift methanol out of methanol, when the methanol is heavier? Well, yes, the methanol is heavier. So that is not the answer. Let's go here. What kind of bonds do we have? Well, between water and water, the hydrogen bonds. It's H-O. Well, that's true for methanol as well. So the nature of the bond doesn't help us. It must be the number of bonds. So while alcohols only can form 3 hydrogen bonds per molecule, water can form 4. Because this R will be replaced by an H. And that can be involved in hydrogen bonding with the lone pair of electrons on the O of an alcohol. So let me make a point here, and then we'll stop. Understand what this means. Because of the difference of 1 hydrogen bond from water to methanol, I have a 35-degree difference in boiling point. That is the impact of losing or gaining, however you want to put it, 1 hydrogen bond. 1 hydrogen bond causes a 35-degree difference in boiling point, even when the other molecule is almost twice as heavy. So how potent must the hydrogen bond be? And the answer is very potent. So other than ionic bonds, hydrogen bonds are the strongest forces that we will need. Because again, ionic bonds are not intermolecular. But of the intermolecular forces that we will meet in this course, hydrogen bonds are king. Right? They are much, much stronger and have massive impacts in physical properties. Melting point, boiling point, state, and so on. Okay, so we'll stop here and we'll pick up next day.